Question number 1. Two balls are thrown, one in the upward direction, the other downward, with identical 10 miles per hour speeds. Which ball, if any, will hit the ground while moving faster? Ignore the effects of air friction. So, we got two balls moving at identical speeds. One of them is moving in the upward direction, the other is moving in the downward direction. And so the question is, which one is going to be moving faster upon hitting the ground? So which one is going to have a higher speed? The short answer is both of them will have the same speed, because gravity is going to have the same effect on all falling objects. The one thrown in the upward direction is going to slow down to a stop, and what goes up must come down. So upon returning back to the same point, is going to have an identical speed to the one which is thrown in the downward direction, so which means that both of them are going to be moving at the same speed. Question number 2 says we got a ball thrown in the upward direction. You know that ball is going to momentarily come to a stop before coming back down. So the question is the ball accelerating at the moment it stops? Well, is it moving before it stops? Is it moving right after it stops? If it's moving before it stops, obviously it's accelerating. If it's moving right after it stops, it's obviously accelerating. So about a second before it stops, it's moving. So it's going to go from 0 to 10. So the acceleration is going to be 10 meters per second squared. And then right after it stops, it's going to go from 0 to roughly about 10 meters per second within the next second, which means that it's also going to be accelerating. So the acceleration is how fast the velocity changes in time. If one of the velocities is 0, if the other one is not 0, it's always accelerating, which means that this ball is accelerating even at the moment that it stops. I mean, you can literally take that moment and break it into smaller and smaller time periods. So the question is this: is it moving like a trillionth of a second before it stops? The answer is yes, so it's accelerating. Is it moving like a gazillionth of a second after it stops? If the answer is yes, of course it is still accelerating. So just because something comes to a stop at some point within its motion does not mean that there's no acceleration. On the contrary, because it stops from moving, it's accelerating. And because it goes from 0 to something else, because it starts to move after it stops, it's also accelerating. Right, so the question number 3 says, which ball accelerates more rapidly, the one which is dropped or the other one which is thrown in the downward direction? Well, both of them will have the same acceleration. Once the ball leaves your hand, gravity takes over. When gravity takes over, the acceleration remains constant. The one which is dropped is going to go from 0 to 10 meters per second within the next second. So the acceleration is still 10. The other one, which is thrown in the downward direction, is going to have an initial speed. So that speed is going to increase at a constant rate of 10 meters per second each and every single second. So whatever that initial speed is, whether it's 30 miles per hour, 50 miles per hour, 100 miles per hour, during the next second, it's always going to be moving at a speed which is 10 meters per second larger than the previous speed that you had. Question number 4, we got the space shuttle traveling at 17,500 miles per hour within 8 minutes after its launch, while traveling a distance of 180 miles. So, given the fact that no human pilots the space shuttle during launch within that 8-minute time period, NASA needs to make motion predictable. So the question is, how does NASA make motion predictable? It's the same question. How do you make motion predictable? What is it that you need to know? What is it that you need to do in order to make motion predictable? The short answer is you have to eliminate jerk from motion itself, which means that you got to make sure that the acceleration is not changing, which means that you have to fix the acceleration to a constant value. So when you fix the acceleration to a constant value, a couple of things become predictable. Number 1, the location becomes predictable at a given point in time. So if you know that it's been 8 minutes, and if you fix the acceleration to a constant value, you would know, if you have the right acceleration, that the space shuttle should be 180 miles from the surface of the Earth. So the location becomes predictable. What else becomes predictable? The speed at that location as well as at that time becomes predictable. So if you know the location, it's 180 miles from the surface of the Earth. Space shuttle should be moving at 17,500 miles per hour. If you know the time, it's been 8 minutes. The space shuttle should still be moving at 17,500 miles per hour. Last question referring to John Stapp. What do we know from John Stapp experiment? We know from John Stapp experiment that you can survive up to 20 to 25 Gs up to a few seconds. So up to a few seconds, 1 second, 2 seconds, 3 seconds. If you're exposed to 20 to 25 Gs, you should be able to survive them. And then the question is, given the fact that Princess Diana's car experienced about 22 Gs, why then did she die? It just doesn't make sense. I mean, if you can't survive up to 20 to 25 Gs, why would you die if you're exposed to 22 Gs for a tenth of a second? That's absolutely nothing. It should be very survivable. The fact that she did not survive this means that her impact time wasn't the same as the cars. All right? For someone to die on impact, that implies that the acceleration had to be more than 140 Gs. If the car's acceleration is about 22 Gs, and if you end up getting 22 Gs of acceleration from a crumple zone, which is going to give you a tenth of a second, which means that the Princess Diana was not sharing the same impact time, which means that she was not wearing a seatbelt. If she was not wearing a seatbelt, her impact time must have been much, much shorter than the car's impact time. So which means that her acceleration was extremely large. More than likely, it was more than 140 Gs.